So in the last video we described an idea for starting with an injection from 5 to 3 and then getting a contradiction by iteratively applying some procedure where at each step we get injections for lower and lower natural numbers until we get to 0 on one side in such a way that it's clearly a contradiction. This iterative process of reducing one case of a thing you're trying to prove with certain natural numbers to other cases with lower natural numbers, this can basically be carried out in a rigorous argument by doing induction. So you may have gotten the sense that here this is like carrying out an induction step, reducing to a lower case. So in induction, you get an induction hypothesis which says assume you have the lower cases and then you get to try to prove the upper cases, the higher cases using the lower cases, right? So this whole idea is screaming induction. So let's be clear about what it is we are going to prove by induction. In the statement of mathematical induction, there's this proposition, phi, that shows up. What will play the role of that proposition? Well, we have two choices of variables to do induction on, n or m, and I'm going to choose m to do induction on, this one. So what we're going to prove by induction is that for all m, if m is a natural number, then here's the statement about m that I'm going to prove by induction. And you might see that I'm leaving a ton of space here because notice I did not actually fix, well, I did fix n. So let me delete this statement, suppose n and m are natural numbers. I actually don't want to fix either of them. And let me change my ultimate goal. It's the same goal, but I'm just stating it differently. I want to prove that this is true for all natural numbers n and m. Let me space that out a little bit better. All right, so I want to prove for all natural numbers n and m that this is true. That's really the statement of theorem 122, right? N and m are free variables in this standalone statement, theorem statement. So there's really an implicit for all n and m here. So this is really what I want to prove. And when I state it this way, I'm not fixing n and m at the beginning of my proof. Now, I told you I'm going to do induction on the variable n, on this variable, but you might expect, if I'm going to do that, that I would fix n and then write down what I'm going to prove by induction on m. No, instead I'm going to put a for all n in the statement that I'm going to prove by induction. So let me make the statement that I'm proving by induction be in a different color, like yellow. So I'm going to prove that for all m, that for all n, that we have this thing. So so basically this is my phi, right? Or usually we would put, or what I've been doing is putting x in certain places. So x here, x there, just to compare with the x showing up in the statement of theorem 94. In this statement of this theorem, x is the variable that gets replaced by various things in the base case and in the induction step. So the x is the position of the variable that we're doing induction on here. So the base case will be to prove this, but with a 0 in place of the x. You see how this is a little bit more complicated than what we have done before with induction? It's still an induction, but normally, I don't think we've ever run into a situation, in the lecture at least, where the thing that you're proving by induction, the phi itself, has a universal quantifier in it. like, yeah, in the statement of induction, you're trying to prove these universally quantified things, but phi doesn't contain another universal quantifier usually, but here it does. What you might be more used to when there's two variables is, on the outside, we fix a natural number n out here, and then our phi is just this part, right? We wouldn't have this. We would just put this would be our phi. But you will see why in this situation it's helpful to make this your induction, the thing that you're proving by induction. Make this your phi. Actually, I'll tell you right now, it's because of the induction step. In the induction step, you get to assume the induction hypothesis, right? If you stick the for all in here at this level, then your induction hypothesis contains the for all in it, and it ends up being a stronger induction hypothesis, and we will need that in this proof. Base case, we must prove this, right? But with 0 in place of the variable that I'm doing induction on. So the base case is a for all statement. So to start proving the base case, I should consider any natural number n. See, this doesn't usually happen when you're writing an induction proof, right? You don't have to prove a universal in your base case, but it's happening here. So consider any natural number n. Then okay, one thing. I'm going to make a modification here. So we actually I left it over here. In a previous video, we already proved the leftward implication of this whole theorem, right? So sure, this is our ultimate goal here, but we've already proved that n less than or equal to m implies there exists an injection n to m. So let me write down here, instead of the ultimate goal, the remaining goal, the remaining portion of our ultimate goal, and that's to prove the other implication. So this one, that's what's left. So that's actually what I'm going to work on proving by induction. Without induction, we achieved the leftward implication. Okay, so now I get to assume, now I'm only proving one direction here, I've already got the other direction without induction. So now assume that there exists an injection n to 0. So then, existential instantiation, we can get an injection. So get f mapping n to 0 such that f is injective. Now, the base case, this is what we iterate down to in our plan earlier, right? So like, here was my picture. We started with like 0, 1, 2, 3, 4 here, 0, 1, 2, 3 here, and then we kept making modifications and reducing the situation 5 injects into 3 into lower situations. 4 injects into 2, 3 injects into 1. And then we got down to a base situation. The base situation is something injecting into 0. So, oh, by the way, you see why I chose to do induction on m rather than n? It's because I want this to end up being my base situation. So, something injecting into 0, we're now proving that that's not possible. So whatever this reduces down to, the base situation I want to prove is not possible. At least not without n being less than or equal to 0. In my plan earlier, I was framing things as proof by contradiction. Maybe I was being confusing here. We're not after a contradiction right now. We didn't start a proof by contradiction, right? We are just assuming there's an injection n to 0, and we're trying to prove that n is less than or equal to 0. Or you could say we're trying to prove that it's contradictory to have not n less than or equal to 0. So that was the contradiction we were seeking in the plan earlier. Okay, well, I think we've run into this situation before, I think in the previous lecture, where we had a function from a set to 0 0 is the empty set. And so we were like, well, if there are any elements in this set, then f has to send them to elements of this set. But if this set has no elements, then that would be contradictory to be able to send things into there. And so this set must not have any elements. And we could write that, but I think we came up with a better way of writing it. So I'm just going to repeat what we did last time here. So we actually used this idea that if you've got a mapping, f maps x to y, then you're looking at a subset of the Cartesian product, right? It's like a set of pairs where each pair's first component is an element of x and second component is an element of y. So by theorem 55, which I would write down if I were typing this up and showing it to you, but since I'm speaking it, let me save some time and not reference things explicitly. But I'm saying by theorem 55, f is a subset of n product 0, which is n product empty set, by the way. And a product with an empty set, let's see, there's a result about this over with Cartesian products. Here. No, not that one. This one, Cartesian products and emptiness. Yeah, a Cartesian product is empty if and only if either of the Cartesian factors is empty. I don't know if that's what they're called, but yeah, so this is the empty set. So f is a subset of the empty set. So then by the minimality of the empty set, f equals the empty set. So then the domain of f is the domain of the empty set, which is the empty set, which is 0. Oh, and by the way, let me shift this over. By the way, n is the domain of f, right? F maps n to 0. So n is 0. Therefore, it's less than or equal to 0. So thus, n is less than or equal to 0. So that's just like a slick, quick way to make what I think is the more intuitive argument is to say, like, look, this is empty, and f maps the elements of this to there. So if there are any elements in here, then you've got elements there, which are the results of applying f to elements here. So there must not be elements here in the first place. All right, so that's it for our base case. And the induction step, that'll be the hard part. That's where we have to do, from our plan, the sort of rewiring that we had to do to reduce one case to a lower case. So how about before I end this video, I'll just set up the induction step. So what do we need to prove? So let's see. I'm doing induction on m, right? So suppose m is a natural number, and assume an induction hypothesis. So assume that we actually have this here. So that's my induction hypothesis. And then what do we need to prove? This, but with m plus 1 in place of m, right? Or next m, however you want to write it. So now we must prove that, and then the same thing here, duplicated without extra letters, but with the m's replaced by m plus 1s. Let me make space for that. And yeah, of course you could write next m here rather than m plus 1, but like I mentioned before, now that we know that next m and m plus 1 are the same thing, I prefer writing it like this. So I hope now you're seeing the potential value, at least, of including the for all n quantifier in our phi, in our proposition phi that we're doing induction on. So the potential value here is that in our induction step, we get to assume this for all n statement, which is much stronger than just assuming this little statement for a particular n, right? So if I hadn't included the for all n in the phi that I was doing induction on, then this would be my induction hypothesis and I'd have to prove this. So it's kind of a trade-off, right? Like I'd have a weaker hypothesis to use and a weaker thing to prove, so that sounds easier. But including the for all n, I have a stronger hypothesis to use, but I have to prove a stronger thing here. It turns out that this way works while the other way doesn't. Okay, so let's see if we can carry out the induction step, that iterative procedure, in the next video.